Well, it's my pleasure to welcome everyone to the Infinite Games Workshop. This is the last meeting this semester, and we're going to be having Matthew Bolan speak about the fact that every countable ordinal arises as a game value in infinite chess. Matthew is a first-year grad student in mathematics at the University of Toronto, and I'm really excited about this talk because this is answering a question. This theorem that he's going to present is a sort of culmination of a lot of work that's been going on for many, many years. When I first got into infinite chess, then we had positions with value omega, and then omega squared with infinitely many pieces, and then omega cubed, and then with Corey Evans, and eventually we got up to omega to the fourth, and so on. And of course, we were aiming at bigger and bigger ordinals, and we really wanted to prove that every countable ordinal would arise. And I conjectured that, in fact, that would be true. But we were only ever able to prove that for 3D infinite chess because we needed to fit the well-founded trees into the position, and we couldn't ever make them fit in the plane, but we could if we had another dimension. And then Davide and I, of course, proved the corresponding theorem for checkers. And so now here we have today the Matthew Bolan is going to tell us every countable ordinal arises as the game value of a position in infinite chess. So go ahead, please. Thanks.
All right. Well, thank you for that introduction. I think I'll get started. So first, we're just going to quickly review what exactly we mean when we say infinite chess and game values in infinite chess. So, infinite chess is the natural generalization of the rules of chess to be just played on the integer lattice instead of the 8x8 board. Knights and kings move as you'd expect. Bishops, rooks, and queens we allow to move any unbounded distance. They should still move some finite distance, of course. We ignore any fancy pawn moves like double pawn moves and promotion, at least in all the positions relevant to this talk, and castling as well. This won't be relevant for us. Checkmate and stalemate are defined as you'd expect. Maybe sometimes stalemate is defined as, maybe sometimes people say that the win condition is that you should capture the king, but for me, this distinction should not matter. And similarly, the 50-move rule is usually ignored, but again, for my positions, actually the 50-move rule doesn't matter whether we assume it or not. And so the difference between the talk that we had at last meeting and this talk is that my positions are going to have infinitely many pieces on the board. This is going to give us a lot more room to fit in trees, of course. It's a much easier prospect to hide a well-founded tree when you have infinitely many pieces, one so that you can, make nodes of your infinite tree correspond with actual physical pieces on the board instead of some weird program for it. And then just some conventions. In all the diagrams I'm going to show, the white pawns will be going up the board, and you should assume that the diagram is like part of the infinite board. It's not, the borders of the diagrams are never real. There's always infinite space on all sides. Okay, and then just quickly to remind us of the definition of game values, we say that a position is game value 0 if black is to move and is currently checkmated. If white's to move, then we give the position game value alpha plus 1 if alpha is the minimum game value white can move to. And finally, if it's black to move, and black can only move to positions that have already been assigned game values, then the position is the game value, is the supremum of those game values that black can move to. And so positions with the game values are known to be precisely the positions which are winning for white. And in the game values have a natural interpretation as the distance white is away from winning the game. So in particular, in the finite board case, the game value is always a natural number, and you can interpret it in the finite board case as saying white has mate in n. In the infinite case, there's no reason that this supremum in the definition should be over a finite set. So in particular, the new phenomena is that transfinite game values may occur. Okay, so if that's clear, I think we can move on to the actual construction and stuff. Right, so what are we answering today? So we're going to define the omega 1 of infinite chess, and I've put a little tilde on top of the chess to indicate that we're allowing infinitely many pieces. You wouldn't write that for the finitely many pieces, I think is the convention. And then we define this to be the supremum of all ordinals, which actually arise as a game value. And there's a trivial upper bound, which is that this omega 1 of chess is less than or equal to omega 1, basically because at any point in a game of infinite chess, you only have countably many moves to select from. So the supremum is always over a countable set. So when you do the induction, you can't ever escape the countable ordinals. So, and so there's a known lower bound, right? So there, as Joel said at the start, there's been a lot of work in establishing lower bounds. And there's a paper by Evans, Hampkins, and Perlmutter that establishes in particular a position which has mate in omega to the 4, maybe plus k or something, but around omega to the 4. And but the purpose of today's talk is that we're going to show for every countable game value, or at least, well, first for arbitrarily large countable game values, but then every game value follows, that there exists a position with said game value. And so the way that we're going to do this is going to imitate very closely the idea used to prove the result in 3 dimensions. So in 3 dimensions, they're able to, Evans and Hampkins, hello, they were able to get this result by, for any well-founded tree, they were able to create a position such that, so let me draw a well-founded tree, right? So you might have something like this, and so on. And they made a chess position such that playing through this chess position is like walking down this tree. And so the black king walks down the tree, node by node. And if black ever runs into a dead end, like say if black turned here, then in the leaf node, the black king would be mated. And in this way, such a game, it's a well-founded tree. So eventually, there's no infinite branch. So eventually, black will wander into a leaf node. But the game value of this position is then greater than or equal to the rank of this well-founded tree. And as, of course, well-founded trees exist of arbitrarily large countable ordinals, that gives the result. So the way that they did this was they had sort of a series of pawn tubes that the black king would go down. And the way that so you could think of like once you enter a new pawn tube, that's like entering a new node. And upon entering, a bishop would move down an entire line, is my recollection, and this would open up a door to a chosen child node. And then the black king would have to walk down this pawn tube and then take the exit, which black had just opened for themselves. And in this way, the construction worked. But the issue with this was that you really needed these bishops. Bishops move along straight lines, so you had to make these pawn tubes very rigid, very straight. And at the same time, you needed these pawn tubes to contain the black king, to ensure that it stayed walking down the tree. And so sort of my solution to this problem is that we're going to remove the need for the pawn tube part of that construction by having the king stay stationary. And we're going to somehow get the entire tree structure to work using only bishops, where you don't, where bishops move to where they're going instantly, so they don't need any infrastructure on the road to keep them contained. And so just to orient ourselves, this is a blueprint for what I'm going to be building, okay? So this is a diagram of how I would build a tree of countable depth, having countably many branches at each node. So you should think down here is the root. On the first move, a black bishop will move up along this line and will stop at one of these squares. At one of these squares, the position is such that black will then be able to move a bishop. Some sequence will occur here, and at the end, some bishop will fire out to the upper left. These circles are a mirror image of this. So if, say, black had instead gone over here, then at this circle, black could stop at this circle, or presuming maybe there's another circle up here. At this circle, black will be able to turn right and fire a bishop out this way. And why black has to keep moving the bishops like this will be something that we'll understand in a moment. But I just wanted to show that there's this sort of structure. And this circle is a mistake, by the way, I'm sorry. But yeah, the main thing to understand about this is down here, below the entire position, is this box that is going to contain the black and white kings. And outside of this sort of upper quarter of the plane is entirely blank space. So in a lot of our analysis, we're going to need to argue that black's bishop will be able to give black an infinite source of moves. So it's important that we have enough blank space out here for the black bishop to evade finitely many white bishops. So keep that in mind. Okay, is that clear? Because now we're going to move on to actual chess positions. Okay.
Could you explain a little bit more about the distinction between the squares and the circles, or just the...
Yeah. So the squares and the circles are just mirror images of each other. So a square, a bishop can either choose to pass through or stop there, after which some finite sequence of play will ensue, and the bishop will emerge going to the northwest.
Okay, so you mean they're going to serve the same function in the position, except that they're oriented in...
Yeah. Okay. In practice, we don't even need to do any more work. We just need to flip all the columns of the position.
Okay, thanks.
Yeah, sorry. Okay, so here is the actual box down below the rest of the position that is going to contain the kings. And this is how we're going to force black to obey this plan of like moving through the tree only. So let's understand what's going on here. I call this the white court because it looks kind of, you have the white king and queen, and black's king is sort of imprisoned. It's been captured. So the situation is quite dire. But if you look at this position, you see that, these white bishops are frozen. All these white pawns are frozen. These cannot move. If white's never able to take these black pawns, white can never free up this outside of the court. And in the meantime, white can try and move these rooks back and forth and the king and queen back and forth, but can make no progress towards mating the black king unless black cooperates. So if somehow black is ever reduced to no legal moves outside of this position, in chess, you're compelled to move. There's this concept called Zugzwang, which is when all your moves are bad for you, but you're still compelled to move. And so if black ever has to move, black's only legal move will then be to take this pawn, after which the demise will be swift. So this sort of dictates how play is going to go in this position. So the takeaway is that if black ever is left with no moves outside of this court position, black is going to lose almost instantly, at least 4 moves. Maybe there's a faster mate than the one I just showed. The court was held in place by 3 black pawns on light colored squares. So we're going to take care to only give white dark squared bishops, which cannot take those pawns on light squared bishops, which cannot take those pawns on light colored squares. And we're also going to take care that if we give white any pawns, we place them above the court as well, because a pawn above the court cannot influence the stuff below it. So in this way, we can really guarantee that white's only winning plan is for black to cooperate. And then the final point, I should have mentioned this. So back here, the king has a square here. And this is just so that white has some sorts of waiting moves. There's going to be a number of lines where white will reduce black to just finitely many moves outside of the court, and white wants to just wait until those finitely many moves are exhausted. And that's just to guarantee that we never need to think about those lines if white has those finitely many moves. Okay. And so now here's the position that was a square on the earlier diagram. So a comment is that this is sort of the root node of the entire tree. This will not appear in general. So most of the squares and circles that on the diagram will not have this part of the position, which I've just boxed here. This is just so that I can initialize the position. And yeah, so let's understand what's going on here. So it's black to play. And the key point is that we said, okay, if black ever has no moves outside of the court, then black will lose. And the position is arranged such that the only free piece is this bishop here, right? So I've just boxed it. And right now, this bishop is underneath attack, right? If black, if it were white's turn, white would just capture this bishop, the black pawn would move, and then white would make a waiting move, the black pawn would move, white would capture it. So this is a dire situation for black. Black must do something about this. And of course, black's only mobile piece is the bishop, so black is compelled to move it anyway. Okay, but where to move it to? Well, if black moves the bishop, say, to an undefended square, like here, then there's this white bishop down here on b2 that will then just capture it. And now black has no moves outside, and black will lose. So black must move to a defended square if black is to have a hope, because black's only options to move are along this diagonal. So the bishop can always capture it next turn. So the black should move to a defended square. So the defended squares, there's one right here. And you should imagine in the upper right, potentially infinitely many more. So you see this diagonal is clear. We could place copies of this position on the right-hand side up into the right, potentially infinitely often. And that's how we give black the countably many choices that we need to create these trees.
So we should imagine this first black bishop as the one that's sort of coming in because it has been fired out from an earlier square in the inductive case.
Exactly. If I had more room, instead of this configuration here, I would have essentially a copy of this configuration on the right that has just completed the line that I'm about to show you. So we'll see that later when it makes sense. And that's just so that you don't need to analyze the start position separately than that. But yeah, that is correct. Okay, so let's go through the main line here. I'm going to try to, in this first pass through the main line, I'm going to try to address everywhere that black can deviate. And we're going to address everywhere that white can deviate up to an assumption that white letting the black bishop escape is very bad. And then later, when we understand the geometry position a little bit better, we'll see that that's indeed the case. So this is black's only move locally, is to move this bishop here to this defended square. White really must capture. If white doesn't capture, right? So if white doesn't capture, so if white, say, plays a waiting move, it's not, all these squares are undefended. So then black will simply move off here and then move down to somewhere square over here and then escape to the bottom right where there's nothing but empty space. And after that point, white can spend as much time as they want freeing some finite number of bishops. We'll see that white won't be able to catch black. So white really must capture. And now the analysis starts getting very easy for black's moves because black has only one legal move, which is to capture the bishop. Well, okay, black can also lose in the court, but this is the only sensible legal move. And now white pushes this pawn. And so this construction on the right is a timer that's going to release a white bishop in time to stop black from escaping. And white really must start this timer now. We can talk later about what happens if white starts a timer in some other node, but we'll see that it's just a very bad idea to do anything but start this timer right now. It's a race, and I've arranged it so that it's very close. So they take turns pushing these pawns. At this point, white might choose to capture this pawn, but then black will simply advance this pawn, and this black bishop will be freed, and it can move up here, and then down into the left, there's no obstructions, and it will be out on the open board, will be unable to be caught. So it's a really bad idea for white to capture this pawn, especially with this bishop timer so far behind. White has no bishops that they can free in time to even hope to stop that plan. So black, and similarly here, there's another line. If black captures this pawn, this is a very bad idea because white will simply make a waiting move and then black has no legal moves left. So this is a huge blunder to capture there. So black should push past. Play continues a little bit. For similar reasons, white should not capture in this position, as then black would capture back. And then, white's bishop over here is still 8 moves away from being freed. So black will have more than enough time to move this bishop here, move it to the upper left, and escape to the lower left. So white cannot capture. And likewise, here black pushes past. If black instead were to capture this pawn, that explains the point of this box down here. This is just a pawn catcher. White can make waiting moves, and black's only pieces that can really move are these 3 pawns, and they'll eventually all collect up on the pawn catcher, and black will be left with with no moves, and will be forced to die in the court. Okay. So black must push past. Black cannot capture. And then again, same analysis as always. If white captures now, black will capture back. And black threatens to move this pawn, move this bishop to the upper left, move it to the lower left. That took 4 moves. White has still more than 4 pawns than white needs to free any bishop. So white can do nothing to stop this plan. Okay. So white must still push the pawns. And now black must capture. Again, there's another branch here. What black could push the pawn past, but this is a terrible idea. Black will be out of moves in 2 more moves. So black captures. And now both sides' moves are relatively forced. Right here. So now black has finally managed to free up this bishop. There's a square that's free. And black can move it somewhere along this diagonal. Moving to this square is terrible. This pawn will just capture. And again, these 2 pawns are not a source of infinitely many moves. Likewise, capturing this pawn is terrible because white will capture back and then, again, finitely many moves. So black moves to the only unprotected square. White is just in time to unleash this bishop. So to stare down this diagonal. And now we have a situation very, very similar to how we began. Before we started with a black bishop here that could not move on any diagonal but one, and a white bishop behind it. And the black bishop had to move somewhere down to a protected square. And here we have sort of the same scenario. There's a little bit more analysis to do here, which is this black bishop. We want to say that it has to move to the northwest. So just quickly, if it moves here, if it moves to this square, because this is a new defended square, then white will just capture this black pawn will capture back, and black will be left with finitely many moves. That does not work. Black could also try. I mentioned this because this is sort of an early version of this position failed to this idea. Black could try and retreat back into the little cubby, but then white will just make a waiting move, and we'll have essentially this position, but with this pawn gone. And now black has no defended squares to move to. So black will lose after white just makes a waiting move. So black really must, if black is to win here, if black is to survive longer here, black must move off to the upper left, where if this is a leaf node, there will be no safety to the upper left of this position. And if this is, if this node actually does have a child node, then there will be a child node waiting somewhere, or potentially infinitely many child nodes waiting in the northwest. Black can select one of them, and then we continue the traversal down the tree. Okay. So that's really most of the analysis for the node, right? So what I just showed you was essentially this square position. You should again, in general, those squares do not have this weird thing in the bottom left. So there's nothing like in the way of the diagonal. That's just to get the position started. And yeah, and we can arrange these positions in such a way that we have a countable tree with, countably many branches at each node. If you care, this first line, I've put it like odd numbers, 1, 3, 5, 7, and then, this one is 2 mod 4, and this next one's 4 mod 8. And yeah, and mirroring, hopefully it's clear that you can just mirror. And to build a subtree of this tree, you just don't build the nodes in your tree. And so yeah, and that amounts to essentially the entire construction. But there is still one, yeah, so some quick notes about what we've just seen. In that line, which I just showed, after the main line is done in that node, black has no moves left in that node. So, before we said, okay, black's only piece that can move is this bishop. And that analysis still holds even like once you've passed through finally many nodes. All the black pawns, all the black pawns in this position are completely frozen. And the second point, which is actually very important, because remember at the start, I stated that for white's win condition to only be to reduce black to no moves on the outside, white should not be able to interfere with the court from outside. White should not be able to just ignore whatever black's doing, free a bishop, and then try and attack the court. The point here is that all bishops in this entire tree will lie on the same color complex, essentially because the black bishops determine the color of the diagonal. If they move along, that determines the color of the protected square, and then everything's arranged so that all those colors agree. So as long as you place the root node on the right color complex, then the white bishops are all on dark squares. They're never able to capture the pawns in the court. And the final point is that you could ask, okay, what if white tries to free a different bishop than the one in the currently relevant node? That's maybe something where I can show. I have in Excel, I have a diagram of like what it looks like to chain a few of these positions together. But basically the point is those bishops take about 2 moves to protect any relevant diagonal. And in the meantime, black will just walk out and escape in the same way that we saw in every other line. So, and then the final question is at the very start. So you always have this sort of question, which I already indicated sort of how to deal with, is whether white really needs to capture the bishop here. Because sort of unlike most other lines where white deviates, in this line, black isn't immediately threatening a square on which black can escape. So you have to argue that black can just get out of the local position just a little without being chased down by the free white bishop. But this is sort of the only place where white can deviate and have a free bishop. And so the point is that here I'm sort of cheating by doing it with this starting position. Really, the analysis should be, you should imagine like this pawn chain, but the analysis is the same. The point is that white has no protected squares that white's bishop can move to along this diagonal. So after black moves here, if white's not going to take it, white will need to make some other move. Otherwise, the bishop will be captured and the position will be ruined for white. And at this point, black simply steps off the diagonal. And as long as you space out your nodes enough, black threatens at least 2 squares which have paths to the outside. In practice, the way that I've spaced these out, it's more like 10. But white can try and guard one of them. Black simply threatens the other. And then this square right here is never guarded. So white can't, say, move behind the black bishop to prevent it from escaping to the outside. And then the argument is that once the black bishop is below everything relevant in the position, white can only ever free finitely many bishops. So, even if like white moves a bishop onto the same diagonal as black can just move onto some diagonal which contains no white bishops, always, just always proceeding downward. So really, white should take great care never to let the bishops escape. Okay, and yeah, and so that's essentially the construction. A quick comment is that if you instead ask about just countable positions, right? Not countable, computable positions. Then I think the same construction should tell you that the omega one of, you know, computable positions in infinite chess should be the church clean ordinal. This is essentially because, you know, you repeat this construction, but instead of saying countable tree, you say recursive tree. And you know, recursive trees are, of course, their ranks are cofinal in the church clean ordinal. So sort of the thing which made this particular idea tick was the zugzwang theme, right? At all points, the way that we forced black to keep moving through the tree was that black had no other moves, and that if black ever ran out of moves, black would be forced to sign their own, you know, death warrant. So I initially, when I came up with this vision, I thought this idea was more important than I think it actually is. But still, sort of the point is that I can avoid having the king walk through the tree by using the idea that black is compelled to move to communicate the fact we've run out of tree, back to the black king, back to the win condition. It turns out that you can probably just do this construction with where the bishops threaten to escape and just checkmate white in one move. And that gives you a larger position, but it seems still possible. So the zugzwang was less important than I thought, but it's still a comment that sort of the reason for the pawn tubes initially was that you need the win condition in the leaf nodes of the tree. And this is a way to put the win condition in the leaf nodes of the tree without putting the king in the leaf nodes of the tree. And then the final comment is that I made this all in Microsoft Excel. We can go to Microsoft Excel to explore a few of those lines, which I drew with arrows, but if there's questions. But I'll just say that if you're designing, you know, even like moderately large positions in infinite chess, I found Microsoft Excel to be like a very good tool. You can set the column width to be the same as the row width, and then you have an infinite grid. You can copy paste stuff and save it anyway. But yeah, so there's my sources, but that's about it. Thank you, everyone.
Well, thank you very much. Fantastic. So are there any questions? I have a number of questions, but if someone else has a question, that's fine. Any questions?
Sorry, is my microphone working?
Yes, everything's fine. Is that Jade? Yes.
Yeah, that's me. Sorry, I'm a bit congested. Well, yeah, that's very interesting because I always was also wondering about like what was this? What's the kind of limit of game values? I mean, I was trying also to find a bound on like the thing with finitely many pieces, but I didn't actually really get very much. So I think that was very cool. Good job. I was also, I mean, it's not really a question, but I was kind of just wondering how this stuff might be related to like descriptive set theory, because like the idea of like infinite well-founded trees also could be related to like analytic sets and Susan representations or whatever. So maybe there's some kind of cool parallel between that, but I don't really know.
Yeah, so there's a version of this position which I didn't quite show just because it's a little bit too large and it's sort of only 99% done instead of 100% done. But if instead of just black moving the bishops through this tree, you make the position a little bit more symmetric, like I described, where black is threatening a mate condition, then you can imitate basically the same construction with white. So you can have a position where a black bishop is inputted, and then somehow a white bishop comes out. And then the and you have it symmetric so that both the black bishop threatens mate and the white bishop threatens mate. And that lets you, instead of just putting in trees, it lets you put in sort of some large class of Gale Stewart games. So descriptive set theory came up for me there because, well, once you have a large class of games, you want to describe, you would like to describe the complexity of the winning strategies in those games. So you can make computable chess positions in which maybe I mean, already Joel's paper has a position where I think white has a winning strategy, but no hyper-arithmetic winning strategy. But you can make, but once you have arbitrary Gale-Stewart games, you can make a Gale-Stewart game where a player can win if and only if they can decide membership in some hyper-arithmetic set, an arbitrary, yeah. And so that's a certain completeness result. So if you just do that sort of tweak to get both white having infinitely many options and black having infinitely many options, you can explore that side of things, the computability aspect and all the light-faced hierarchy of sets and all that. But
yeah, that makes sense.
So
infinite chess is an open game, right? The payoff set is okay because draw is like infinite.
Yeah, the drawing condition in infinite chess is not necessarily open, but winning always is open for both players.
The ordinal game value analysis only makes sense for open games. I mean, you can't define the game values if it's not open.
Yeah.
I mean, you can define them, but only for the sort of open part of it. So, so I have a kind of follow-up question to that, namely, okay, in your position, it's black to move and white is going to win. And you described a way of making it somehow more symmetric. Can you hope to get, because you have a big empty part of your board on the bottom, right?
Yeah.
Is it completely empty, half empty?
Yeah, it's half empty.
Okay, so could you hope to make a position where it was second player win regardless of who went first? In other words, I want it like another part of, I want a position like this. Okay, this is the sort of white's going to win part when black goes first. But maybe we can make it compact or something and use part of the rest of the board to do the duel of that in such a way that the first player who plays is going to lose. But I'm not sure your method would work for that, because in this one, it seems like white often has a lot of moves. He can run his clocks and release his bishops and so on. And so that would totally interfere with the sort of dual side of it, which was based on the idea of not having any moves.
Yeah. So in particular, this exact construction, after a note is done, this white pawn is left with a move. The way that you would try and fix that, and the reason why the other position is so large, is that
but he's got a lot of those clocks that he can move and release bishops with, right? Yeah.
So the way that you can kill two birds with one stone, I'll briefly try and verbally describe this. So you have this sort of pawn configuration here, right? And so these two pawns up here are in this position solely to stop the white pawn from going up and maybe interfering with something like, I don't know. They're maybe not so necessary. So what you do is, instead of having this clock here, you use this white pawn as a clock. So this white pawn goes up and this black pawn goes down. And the white pawn frees something and the black pawn frees something. And both players are basically forced to do this.
So you limit the moves of white also, you're saying?
Yes. And so this is, that now hinges on, that is now, I should say, that particular modification of the position is work together with Andreas, who's here as well. So Andreas, I think, came up with that particular modification. And so depending on how much Andreas comes to share, I don't know if I can show that position, but people sound interesting.
Right. But so then you think that it will work to make it a second player win?
Yeah, I think essentially what I think is the case is that, so what I do think is very possible is for any you modify the definition of Gale-Stewart games to have draws somehow. And then for any Gale-Stewart game with draws, that's open for white and open for black, and then the draw is the complement of their two winning conditions.
Right.
I think that there is a position in infinite chess which imitates that game. And so Andreas and I have been writing that up, and maybe I'll put that up on Math Overflow soon or on Archive soon. But
sounds great.
Yeah.
I have another question, but does anyone else have another question first?
There's something in the chat.
Oh.
Okay, I see. Yeah, Andres, are the pictures in the Google spreadsheet? Can I?
I'm not sure. Let me check.
Okay. So maybe I can show that position instead of just describing it. But yeah, is there more questions?
Right, I have another question, and that is, can you didn't show us the dead end, the terminal node, the terminal squares.
The terminal squares.
Yeah, can you show us that?
Yeah. So
what happens when the bishop shoots out and then it's going, or does it just shoot out into nothing?
It just shoots out nowhere. There's no difference. You could put something in the way if you like, but if there's no safe squares for the bishop to run to, let me find it.
Oh, I see. It just goes into the void and then is captured by the following white.
Exactly.
Okay, I get it.
Yeah. So there's yeah. So I like there being like nothing new, but yeah.
Right. Okay, no safe squares. So the terminal node is just that there isn't any further node to land on. I see. Okay, I get it.
Yeah, probably Black's best play if there's nowhere to run to. Like, I guess this would delay for 5 moves, but I mean,
right. Yeah. Okay. Good.
Here would delay for 4. Going back here, Black plays a move that would delay for 5 again. Anyway, so yeah, but yeah, Black needs a source of safety in the upper left, or else Black will lose in like 10 moves or so. So
all right. Well, fantastic. Any other questions? All right, in that case, let's thank the speaker again. Really fantastic results. I'm really happy to learn about it. Okay, so that concludes this semester's Infinite Games Workshop, and we're going to start again next semester. If you're interested in giving a talk on anything connected with Infinite Games of any kind, please contact either Davide or myself. And next semester, we're going to have a web page and a mailing list, and it's going to be all super professional. And so I hope everyone will be joining us again next semester. So that's it. So thank you, everyone.